Dr.S. Joseph Sekhar. He was graduated in mechanical engineering from Government College of Technology, Coimbatore, and completed master's and PhD in the field of thermal engineering from College of Engineering, Gandhi, Anna University, Chennai. During his 30 years of experience in teaching, research, and administration from various institutions in India and abroad, he has taught mechanical engineering subjects like advanced thermodynamics, heat transfer, CFT, thermal engineering, renewable energy technologies, refrigeration and air conditioning, food preservation technologies, and guided many projects to UG and PG students in India and abroad. He has published more than 60 research papers in reputed international journals. He reviewed articles from many reputed international journals and be examined for an doctoral thesis of popular universities in India and abroad. He completed a research project worth 16 lakhs from AICT, and he had been co-investigator of a UGC product funded project. Currently, he has a TRC funded project and an industrial support research project. His research is focused on eco-friendly refrigeration, biomass-based renewable technologies for rural applications. He is in cooling application and hybrid renewable energy system. Moreover, 7 students have completed PhD in areas related to thermal and energy engineering under his supervision. He prepared and presented the previous 6 year of college to get a grade in NAB-NPA accreditation in 2018. He organized many international conferences, training programs, FDP seminars, etc., with the support of reputed institutions. He had been the resource person for workshops in the field of CFD and alternative refrigeration technologies. Dr. S. J. Sekhar is the fellow in Institute of Engineering, India, immediately past chairman of IET UK Canadian Local Network and member of Society of SE and ISA, IEEE and ISTE. Welcome you, sir, to the FTP program organized by Department of Energy and Environment, NIT-Trichy.
Thank you very much for your introduction. Yes, good morning to everyone. First of all, I thank the NIT-Trichy and especially the Department of Energy and Environment Studies for providing an opportunity to me to discuss about my research to this August gathering. This talk, I am focusing on the performance studies of downdraft gasifier to use the biomasses available in the remote villages. Okay, that's the main aim of my talk. I just want to give a brief introduction regarding how this area of study has a good scope. Followed by that, I will discuss something on the downdraft gasifiers. There are different types. My focus is towards downdraft gasifier. I will discuss why it has been selected for our studies. In the meantime, I will discuss with you the performance parameters. Especially our aim is to enhance the performance. So we studied the performance parameters. I'm going to discuss about that. Meantime, the performance enhancement was found very important. Right now also it is being taken as an important area. There are different methods available for doing so. I'm going to discuss few of those in this area. To study the performance of a biomass gasifier, we have different methods. So we use the analytical simulation. We are using the numerical simulation, followed by that experimental investigation. All these aspects I'm going to discuss. Probably I will discuss a little bit more on the numerical and experimental investigation. If I talk more on any one simulation, it will be taking a lot of time. Therefore, I would like to speak a brief about all those things. Some issues we faced, and if you want to utilize the biomass for gasification, how it can be done through all these analyses, I will discuss. Followed by that, I will state few of my publications. I hope you are already familiar with the need for energy transition, the international scenario, all those things. You are all very much familiar because the first couple of sessions, it was discussed very well by the senior professors. What are the status in India, abroad, all those things you are familiar. Since I want to establish my scope, I would like to say a few words why biomass is going to dominate in the future. If you take this small projection, if you take the projection of various energy resources, the 2020, 2030 and 2050, if you take all these different scenarios, if you take the biomass right now, for all energy usage, it's a primary energy usage, okay, not for power production, it is for all purposes. Together, it is having some around 60 exajoules. If it is going to slightly increase, and if you take in the 2050, it is going to increase drastically. Similarly, the wind and solar is going to increase by 2050 drastically, you can see that. Same time, this is going to reduce. I mean, coal, gas is going to reduce, but not that much. Oil is going to reduce. Some increase in nuclear. Okay, this is the projection we have seen recently. And it is said that around two-thirds of the global energy is met by the renewable energy in 2050. Therefore, the biomass is going to play a major role, right? You can see that the biomass, if you take the biomass curve, it is going very steep. This is mainly due to the potential of biomass in different places. You know, already the per capita energy usage of our country is lower than the international average. If you want to improve the per capita energy usage, naturally the country will develop. All the developing countries, their per capita energy usage is high. So indirectly, I can say that if you want to develop a country, we need to give more energy to the people for a comfortable life as well as to do their profession well. Now, our country is focusing on developing the villages, rural areas, remote places. If you take the remote places, the biomass is a dominant resource. That's the reason the international condition they are projecting. Many rural areas, the biomass availability is high and it is not being used well. Therefore, if it is focused, definitely the energy transition is possible. That is the reason we focused our research towards these villages or remote areas. It has a good scope, okay. And moreover, in some places, especially in our research region, 7 to 8 months always cloudy, we cannot see much sun rays. The average solar energy availability is not that much to have a technically and economically viable system. And it depends on the wind energy, which is becoming very popular, but still that area, some places we are getting very good wind, some area, remote areas, very poor. And moreover, the wind systems are large systems. So in a decentralized power generation or decentralized energy usage, it's very difficult to take these energy sources in a comfortable way. But these remote places are enriched, having enormous amount of bio-waste. The biomass, okay. So those things can be effectively used. It can help us to fulfill the requirement for the energy transition. So that is the reason we are focusing more on this biomass, especially the biomass available in the rural regions. Okay. Take the biomass. If you take the biomass supply chain, we need to hope for a feedstock. Because the applications are different, the properties of biomasses are different. You would have seen that Dr. Lawrence has taken a very good lecture on how the characterization is done and what is the need for studying a biomass, how the biomasses are having different characteristics and their performance. All those things you have seen. Therefore, the feedstock supply is very essential. And the conversion of biomass to fuel. See, the feedstock should be selected properly and the conversion system should be designed well, then only we get a biofuel. If you take the biomass, normally we concentrate more on the biofuel. It may be a liquid fuel, solid fuel or gaseous fuel, whatever may be. So biofuel has to be prepared, then it can be used for energy, any end usage. Either it may be a thermal application or a power generation, whatever may be. Among the biofuels, if you take the gaseous fuel, it has a lot of flexibility. You can use it for any thermal application. You can use it for any power generation without much conversions. If you want to develop some new system or new energy-based system in a rural area, if the local biomass can be used as a gaseous fuel, the complications for the system will be reduced. If you go with the biomass, a lot of issues will come, and the operations issues, everything will come. And most of the conventional systems, either they are using electricity or gaseous fuel or liquid fuel. So if you substitute with this gaseous fuel, definitely the applications can be taken to the rural level. Instead of having a central place and distributing it to different places, we can have decentralized power generation, decentralized thermal energy generation. So that thing is possible if we can convert the biomass into biofuel, especially gas. And moreover, if you take a biomass, if you burn directly, and if you burn through gasification, the energy utilization can be increased 10 to 30%. So definitely there is a saving for biomass. One way, we are giving a high quality fuel. Second way, we are saving the fuel consumption. So those things are possible. That's the reason the biomass conversion to biogas is taken for our, producer gas is taken for our study. If you take the biofuel generation route, there are many routes available. We can go for biochemical, thermochemical. I'm not going to discuss more on those things, okay? So there are many routes are there, biochemical, thermochemical. I'm focusing mainly on the gasification, okay? I'm focusing on the gasification to produce gaseous fuel. You have seen many types of conversion systems. I'm not going to deal much on that. My focus is toward the gasification. If you take the gasification, some basic terms are available. I would like to say, maybe most of you know what is gasification. It's a partial combustion of biomass with oxidation medium to form combustible and non-combustible gases. Actually, the main thing is we are heating the biomass to a particular temperature, either burning some quantity of the biomass or using external heat, whatever may be. We heat the biomass to a particular temperature, and we are trying to make some endothermic reactions. The gasification reactions are endothermic reactions. So those reactions, they need heat. So if we apply heat in the right temperature and the right quantity, we can get gases like CO, H2, CH4 and so on. So that is the main aim of this gasification. Okay, mainly we are using air or steam, sometimes combination of air and steam. Many approaches are there. I'm not going to deal more on those things. Our focus is mainly towards the air. The air is available everywhere. As I said, our aim is to take this technology to the rural area. The rural area, we cannot work with complicated things. We have to work with simple things, available things, right? That's the reason we have taken air as our gasification medium. If you take the gasifiers, there are different types of gasifiers available. Okay. First of all, let me say a few words. What is a gasifier? Maybe just to refresh you regarding to know about what is gasifier. Gasifier is a one chamber where we are keeping the biomass. Okay, the biomass we are keeping. We are drying the biomass, and we are heating it, and some pyrolysis activity is going on. The heat is supplied by this combustion. Some quantity of air, biomass is burned, and that is used for this pyrolysis, then drying. Finally, after that, we are going for a reduction. This is the place, this zone is the one which is converting the fuel gaseous char and other things to a gaseous fuel. So this is what the basic operation. So we are applying temperature by a partial combustion. We are doing all the thermochemical reactions inside. Finally, we are getting a gas outlet. Okay. So this is the medium we are giving fuel. Depends on this reaction zone, we are classifying. It depends on the way the biomass is given to the system, or depends on the reduction zone. We are classifying the biomass gasifier into different types. Okay. Actually, updraft gasifier. This is a updraft. This is the reduction zone is normally above the combustion zone. Downdraft gasifier, the reduction zone is below the combustion zone, and the cross flow means it is a side of the combustion zone. Especially these things are based on the combustion zone. Depends on the type of biomass, we have to deal in a different way to have a good flow. Our main aim is to get a good flow and allow enough time for the biomass to react for the thermochemical reaction. At the same time, collect the ash and get a good quality producer gas without much tar and other things. Then we are using sometimes the fluidized bed and this endrained flow. So our focus is mainly on the downdraft gasifier. As far as our Indian situation is concerned, these downdraft gasifiers are available and it is well suiting to our requirements. So that is the reason it has been selected. So in this downdraft gasifier, as I discussed before, the biomass is fed, okay, from the top. It may be continuous or it's a batch, we will see to that. Then the top zone is a drying zone and second zone is a pyrolysis, combustion and reduction. Actually, the grate is there. This is the one which is controlling the size of the biomass. Okay, if you want to use a big size or small size biomass, accordingly we have to have a different grate size. Okay, then first we fill it. We are burning it partially by supplying a limited quantity of air. Normally we call it as equivalence ratio. We won't send the stoichiometric air. We used to control the air so that the required amount of heat is produced. So this heat can support the endothermic reactions in the reaction zone and the gas leaves. A lot of other factors are there to control the zone temperature, control the ash and other things. Okay, that we will see in the coming slides. So this is what we are going to do. So our gasifier, the downdraft gasifier, it's a very simple device because any biomass can easily charged or loaded in the system, and you can easily remove the ash at the bottom. Okay, we can control the air flow rate, we can control the moisture, so many things can be controlled. So that this is a simple device, there is no complicated operation. That's the reason a biomass gasifier is preferred for rural applications. Already some gasifiers are also available. Okay, and some of the features it has. I'm giving you some more basic things about the gasifier, why we have selected this type of gasifiers in our in research to implement the rural biomasses. The downdraft gasifier, throat type and open core type. Actually, there is a throat section available normally in the gasifier to increase the velocity of the air if it is a forced convection. Okay, we pump air into the system. And it should control the flow. For that we have a throat. If you use powdery biomasses, especially the low particle size biomasses like rice husk or groundnut shell, something or coir pith, those things when we use, these throat section is the place where the flow chokes. Okay, so we cannot get a good gasification. A lot of problems are there. That's the reason we have open core. The throat is not available. The throat is here. No, the throat is in the combustion zone, where there some arrangement is there, but below the combustion zone. So the throat section is completely avoided. Even that the downdraft gasifier, it is possible. We can change. And the recently available gasifiers, we can go for both the modes with solid big size particles as well as small size particles, and we can work for hot gas and cold gas. Suppose we are using it for the heat applications. We can directly use the gas for the heating application without much filtering. Right? Some filtering might be needed, but we can use the latent heat, sensible heat of the gas. Okay, the sensible heat can be used for the purpose. It will not be lost. Otherwise, when we are cooling, we are spending a lot of energy for the circulation of the water and all other things. Then operating of the pressure loss in the filters, all those things we are losing a lot of energy. So if it can be used directly, it is good. Still it is being used in the gasifier applications for heating, especially in the crematoriums, as the gasifiers are used. There directly it is burnt. Then cold gas. It can be used for boilers. It can be used, the gas can be used in the engines. Actually, many suppliers are there. They are supplying engines with the biogas operation or this producer gas operation. Okay, so this is cold gas mode. Cold gas means there are a lot of stages to clean the gas, reduce the temperature of the gas. When the temperature goes down, the tar has to be properly removed, otherwise it will choke the system. There are a lot of other issues behind it, but it can be operated. So by downdraft gasifier, it has less tar content. The producer gas has less tar content, so it is good. But the feedstock flexibility is moderate. The gasifiers are designed for a particular feedstock, and when we change the feedstock, it may or may not work. That is the reason we thought we should take the gasifier, we should work with the different biomasses, with the different methods, okay, so that we can overcome this issue. As I said, it has a low tar content, it has a fuel property which can be used in IC engines for power generation or any application. Moreover, it has a low power requirement to process the feedstock or to run the system. We don't want much power. Maybe around 10% of the power generated may be used for the operation of the system. We have to maintain low moisture content. The producer is normally produced at high temperature. Second thing is the producer gas has high flame temperature. It can be controlled. Okay, normally for good applications, the flame temperature should be around 900 degrees, some applications, then only it can be used. So those situations, this downdraft gasifier is very much attractive because it can produce the gas for high flame temperature, and it can be obtained for different ranges. Maybe 20 kilowatt thermal you can get, or you can get 1000 kilowatt thermal we can get. It can be fabricated with good efficiency. Okay, we can fabricate the system for small power as well as large power with a good efficiency. When we take the operation parameters, we have to control some parameters so that we can play a major role for the energy efficiency, proper gasification, overcome the flow issues, application, end-use application, then quality of the gasification. Okay, so all these things are the major roles, right? For that, we have to control the input parameters. First of all, to make the system to perform well, the input parameters must be controlled well. Input parameters in the sense, the feedstock. So this is our main focus. So feedstock should be properly controlled. Many characteristics are there for the feedstock. It should match as per the design requirement of the gasifier, or we have to suitably modify the gasifier for meeting the requirement. Then moisture. Moisture play a major role in the performance of a downdraft gasifier, especially choking or other things, tar formation, all these things, the moisture plays a major role. So we should study and control. Gasification medium, the inlet air, maybe you can say air, okay, but the temperature of the inlet air plays a major role. The humidity of the inlet air plays a major role. So all these things are to be controlled. Okay, when we are operating the gasifier, some factors we have to control, especially the equivalence ratio. If the equivalence ratio is very high, maybe more combustion. More combustion means we are wasting the biomass. So we should balance the biomass combustion so that it should take only the required heat. If you give more the heat, is efficiency loss. Then operating temperature. It's also very important for gasification. You know, different fuels, they have different type of carbon characteristics, burning potential, all those things. So when we use those things, we must control the temperature. Temperature plays a major role for ash melting, maybe clinkers, or maybe the tar formation, all those things. Therefore, you should operate the gasifier with a proper temperature. When we go for any new feedstock or biomass, we should see to that whether it is being working at the proper temperature. If it is, even though it gives a good gas property, everything, but the temperature is not proper, we know the ash will melt in some places, some parts it will melt and the clinkers will form, it will choke the line. End of the day, after a couple of operations, the biomass efficiency drops drastically. Therefore, we have to take care of the temperature. Then feedstock flow. The feedstock flow is very, very essential. I will show you later some graphs. The feedstock flow disturbance will cause the change in equivalence ratio, the change in the gas production rates, all those things. So we should know how to control the feedstock flow. Inside the gasifier, the feedstock should flow smoothly. Even if you take a pellets or if you go for the strengthening the biomass, sometimes it will expand. Okay, it will restrict the flow. Therefore, the proper flow should be inside. Then only we can control the equivalence ratio. Yeah, normally the equivalence ratio is the relation between the amount of feedstock used and the supply air. If the flow is not good, the mixing won't be proper. A lot of issues will come. Then the removal of ash. We should have a proper grate and proper ash removal mechanism. If you are not doing that, a lot of unburned biomass will go along with that. Sometimes the ash will remain for a long time. It will choke the flow. It may increase the pressure loss. Okay, so all those things will happen. So that is also a factor to be studied. Then the cooling of the producer gas. Normally, some cooling might be needed, depends on the application. So, depends on the application. So, the output gas contains tar and so many particles. Depends on the application, depends on our tubing, everything, or our burner, whatever may be, we have to control. Sometimes just cooling is enough, or a scrubbing is enough. Scrubbing to remove the ash, flying ash, as well as the tar, it is enough to use the gas. Sometimes we have to go for multi-filtering, sometimes we go for ultra-filtering. So all these things depends on the application. Okay, so we cannot say that the gasifier can be applied anywhere. Depends on the application. We should tune the gasifier. Some applications, no, if the calorific value is less than 3.5 megajoules per normal meter cube, we cannot use the gas. The gas efficiency, the gas will provide a very low efficiency of the application. Therefore, we should see to that. If I am going to install a gasifier in a place, means whether that biomass can produce the required value of the calorific value of the producer gas. So that is a very essential one when you come to the application. Okay. Then output parameters is general. The producer gas properties, conversion efficiency, all these things are the general. We can without focusing any application, if you want to test a gasifier, we can test. And we can find out what is the gas quality, what is the conversion efficiency, all those things. So these are the parameters, operational performance parameters to be studied in a gasifier when we are taking that gasifier for any application which is not mentioned as per the manufacturer's specification. Our aim is to widen the application of gasifiers in the remote regions. Still people are using gasifiers for some areas. And still people are using solid fuels, direct solid fuels in some areas. So in those places, when we are taking the gasifier, we should know how the parameters can be controlled. For instance, we are trying to use this gasifier for paddy parboiling. So paddy parboiling is a place where they are directly using rice husk. So instead, if you go for this gasifier, we found a lot of savings, like in many areas. That is the reason we should know the parameters very well, and we should know the characteristics of the feedstock well. If you know those things, we can take it to the required application and our expectation can be fulfilled. Okay, now I just want to discuss some of the performance parameters, methods to improve the performance parameters. Maybe we can control the feedstock properties, as I said. We can do some modification in the design. For instance, we can change the position of the nozzle, we can change the angle of the nozzle, we can increase or decrease the various zone sizes, we can change the dimensions of the gasifier. All these things we can check. If it is a small change and it has a techno-economic viability, we can ask the manufacturers to do the same and we can get it. And we can use catalyst. Many people tried with the catalyst, so it has its own advantage and disadvantage. The gasification medium can be controlled. Maybe we can use preheating. Suppose we have heat at low temperature, We have some waste heat available. We can use it for preheating the gasification medium. We can control the quality of the gasification medium. Then we can improve. The other method is co-gasification. Co-gasification means mixing of biomasses. The main problem we are facing today in the rural application is, suppose we are designing a gasifier for rice husk. It is available for one particular season. Once it is over, it will not be available. The gasifier becomes ideal, or it has to buy fuel from a long distance. It will not be cost effective. So in that situation, we should know how to mix two biomasses available in a local region, or three biomasses. If you mix, what will happen? How to control? Mixing means if you go for a rice husk and if you go for the groundnut shell, they cannot be mixed easily. So all these things, if you do so, we can manage the continuous running of the gasifier. If you take a large application, maybe they have a lot of resources to get all the required feedstock. But smaller applications, if you go, we need to find a method to mix the locally available biomasses to run the system for a long time. Then only it will be a techno-economically viable solution. That's the reason our focus is mainly towards this co-gasification. Okay, so our focus was to work with the downdraft gasifier, and in the case of biomass, we are trying for the local biomass, and we are trying to mix biomasses so that the gasifier can be operated for a longer duration, continuously it can be operated. Similarly, we can use the locally available fuels without compromising the efficiency of the gasification. Okay, that's the reason. In that one, first one is the selection of feedstock. The selection of feedstock is a very essential one. We have to study the availability, the properties. Availability we have to study by making survey. We did surveys in the different regions and discussed with the people. Based on the small industries available, we found the availability of the biomass. Okay, different biomasses we try. Then properties, the characterization is very important. It has to be studied. Then only we know, okay, how its carbon content, how its ash content, whether it is manageable. All those things we can get an idea. Then handling, how to collect. Some biomasses, it is expensive to collect it. Some biomasses, the transportation cost is expensive because these are all bulk density. These biomasses are bulk density components. If you take a rice husk, if you take a big sack, it may be 10 kg or 15 kg. So we have to collect, store, transport, all those things, issues are there. So those things we have to study. Then cost. Okay, many biomasses are available. Sometimes they may not be cost effective. All these factors are to be studied. And the point of characterization, I am just putting a table here. It shows that some biomasses having high ash content. Sometimes, the previous reports, people say 14%, 20%, 25%, let it be. What I would like to say here is, depends on the location, depends on the type of plant, the characterization property will vary. All the content, the carbon content, hydrogen content, oxygen content, as well as the ash content, all these things vary based on the places. Therefore, if you want to do an experiment in a region, you should take the biomass in that region. We have to go for a proper characterization study. Then it will give us an idea how we can use it in our gasification process. Will it be effective? Will it be technically okay? All these things we can study. In a crude analysis says that if the carbon percentage is increased by 1, the heating value can increase 0.39 megajoules per kg. Okay, this is some crude rules. So if the ash content is reduced, it's good. If the carbon content is increased, it's good. So some idea we will get. Maybe the detailed characterization may be taken, but for a basic application, we need to take the minimum study and get some output regarding the carbon content as well as ash content. If you go for the co-gasification, the co-gasification means mixing of 2 or 3 biomasses. One is called primary biomass, other things may be taken as secondary biomass. Okay, we are mixing them If you take the co-gasification, there are many techniques available. Biomass and plastics, people are doing it to improve the CO or H2. Biomass and biosolids, also it is some places, no, biosolids, they can be converted to biogas with the proper mixing. Biomass and tire. But all these things may not be possible in the rural areas. Rural areas, the only possible thing is biomass. We have different types of biomasses. We can use, we can mix all those things. That is the reason these biomass combinations were selected for our studies. Okay. If you take the biomass, gasification, many studies are available. People tried with the different combinations, different mixing ratios, all those things. But we have taken some thing that whatever is given in red, no, all these things we tried in our gasifiers, right? And we checked how the mixing is going on, whether the mixing will get a good yield or not. For instance, when we tried the coir pith and coconut shell, it was not attractive. Even the rubber seed coir pith, it was not attractive. Even though coir pith has a high calorific value as a solid fuel, it is good, it has carbon content, everything. But when we take it to the gasifier, when we mix it, it is not giving a good result. Okay, we cannot go very deep into the technical aspects of those things, but the practical point of view, it was not, doing well. But some bio waste, when we add, it gave us a very good output. That's the reason we have taken all those things for our studies. These are the biomasses used. And if you take our experimental study, I will explain in detail later. We used 2 gasifiers. This gasifier is a 50 kilowatt thermal gasifier. It is used in the thermal application. Okay, it is used in the thermal application. I will discuss with all the details in the coming slides also. It is mainly used for the thermal application. Okay, we have to load around 40 to 50 kg of biomass. At a time, we have to seal it, we have to switch on the blower, okay, and when the blower is applying proper amount of air and based on our ignition, it start working. Maybe after 25 minutes, we get the producer gas and it will run for 4 to 5 hours, okay. It will run for 4 to 5 hours continuously. Then we have to reload it. We have to remove, we have to wait for maybe 24 hours to cool down. Then we should go for the next loading. It cannot be loaded continuously. It's a one kind of gasifier. It is commonly available, mainly in the crematorium. I think it is available. Some suppliers are doing it there also. Mainly directly it is being used. These are the components. Anyhow, I will explain you later. This is a sectional view of the gasifier. Just for our studies, we made it to a sectional view. Here, no biomass is stored. We have different sensors to measure the temperature. These are the air supply system nozzles, and the grate is here. The producer gas comes out. Okay, so this is a downdraft gasifier. The air is passed through this way. The combustion takes place here. Already we are making a throat section here. So with the help of that, it is doing the gasification process, right? And if you take this one, this is another type of gasifier. This gasifier is a commercial type which has a capacity of 115 kilowatt thermal, around 37 kilowatt electric. This much power it can give. It can run an engine. So it has all the components. I will explain you more the components when we discuss more on the experimental studies. See, this is another view of the gasifier. It can be operated continuously. It has filtering arrangement. It can be used to work with direct thermal mode. It can be used for engines. It can be used for any applications. We have all the control mechanisms here. We can use the hot gas mode, cold gas mode, minimum filtering, maximum filtering. All these things can be done. Okay, so these things I will discuss more in my discussion with the experimental studies. As I said, to approach our research, to use the biomasses in different local regions, okay, we used 3 types of analysis mainly. There are different techniques available. They can call it as analytical methods, numerical methods, experimental methods, economic analysis. Sometimes we use some statistical analysis, okay. Statistical analysis we can use, maybe we use some design expert software like that we can use, maybe it's a combination of experimental and theoretical studies. Likewise, different approaches are there. I'm going to talk about the analytical approach, what we used, the experimental numerical studies in CFD, what we used, and the experimentations, what we have done. Analytical method, it's a very simple method. If you want to try with one biomass, how it works in a gasifier, we can go for analytical method. No need for a high complicated computer system. If you go for numerical analysis, no, we need to have a powerful computer, we need to have the proper software, a lot of things. But analytical method, we can use either MATLAB or you can use Skylab, it's open source, because we used both the software packages. That can be used. Only thing is we have to solve the equations. There are many methods available to solve the equations, and we should know the chemical dynamics, how the chemical reactions are going on, what reactions are going on where, and how it is controlled, what is the kinetic parameters, how the equilibrium conditions can be maintained. All these type of chemical aspects you should know. Mainly it has two major equations. One is a global equation, one is the energy balance equation. The global equation decides the reactions. You know, the energy balance equation decides the temperature and energy, all those things. Here you cannot merge easily both these things, but some techniques we can use to take care of both the things in the gasifier. What it gives is it gives a crude output. Sometimes it can be on par with the experimental results. Okay, for any one, if you want to take a new biomass, already the characterization of the biomass might be available, or we can take it for a characterization, take the basic properties. Okay, then if you know all the fuel properties, based on that we can create a mathematical model. Actually, this is what the model we created. For creating the mathematical model, the main concept is you should assume the things properly. This is the one which is 50 kilowatt gasifier. It's the one for batch processing, assume. This is the 115 kilowatt gasifier. So both the things we tried with analytical methods. Okay, some biomasses we cannot directly use in a system. We cannot put them directly, but we should know how they behave. Okay, for that we can go for this analytical study. The domain should be first created properly, then all the conditions, everything. So we used two-zone approach. People used a two-zone approach, three-zone approach, single-zone approach, okay, and this bulk approach. Different approaches are being used, but it is not a complicated one. A lot of literature is available for these analytical methods. Main thing is we have to understand the basic equations, what is happening in different places. Even presently, you know, we can even iteration, we can go for iteration, we can go for iterative solutions, is possible. We can divide the zones into small segments and we can make control volumes there, and the control volumes we can solve all the equations and we can go ahead. Okay, so this is also possible. Mainly we use the equilibrium based approach in the zone 1. The zone 1 means if you take the picture here, see this is drying zone, pyrolysis zone. Normally the drying zone we cannot easily model it in the analytical studies. We can take the pyrolysis and oxidation zone, but the drying zone properties will be taken care by this, because from here only heat is going, so it will take care of that. Then oxidation zone is there. These two zones we combine together to form a zone 1, because in these two zones the producer gas is not formed well, but the main formation of producer gas takes place in the reduction zone, so we take it zone 2. Mostly this zone, the reactions are endothermic reactions. It means it needs heat for the reaction. That is the reason we modeled into two zones. This is one zone and this is another zone. Okay, So we use different methods. I'm not going to explain in detail about those things. Maybe it may be boring to you, or it may be too much to you. So just we use these methods and we were able to model it. We can use multiple biomasses, even if you want 2 biomass you can use, but some limitations are there, okay. First, after making the model, it should be compared. For instance, I can give you an example from our studies. We used spent tea waste. After taking the tea, we have a lot of waste. So is it possible to use that waste for gasification? That was our aim. Is it possible to use it in a commercial gasifier? Since it has a smaller particle size, if I put it in my commercial gasifier, it will go down immediately. Therefore, we studied that by analytical method, how it performs. Yes, it has high carbon. Already the characterization study says that it has a good fuel property. So we tried with the analytical method. All the basic equations, basic characterization constants, everything we used. And we came to know that it is also fetching a good result, because we compared our results with the previous analytical studies. So we found that, okay, our approach is good. This is a very important one. When we are going for analytical method, first we have to validate our approach, whether it is doing well. Then we can predict. So we found that, okay, STW or spent tea waste, the spent tea waste can be a good biomass for gasification. Once we found that, we know that it is very difficult to use it in an ordinary gasifier. So we should go for the different methods. That's the second thing. First we fixed that this is a good biomass. For that we used analytical studies. Similarly, we used analytical studies for the prediction of the gases. So same study, we were able to predict the gases, how much CO can be produced, H2, CO2, with respect to the equivalence ratio. Usually the equivalence ratio is the predominant factor in a biomass gasifier. All the operations are designed for a range of equivalence ratio, because the airflow vents, everything, and the motor size, blower size, the dimensions, pressure drop, all those things are defined based on this equivalence ratio. So we cannot get any equivalence ratio in a gasifier. There is a range. So if a gasifier is having a particular range of equivalence ratio, we can think how it works. So we checked, suppose if I put this STW in this type of gasifier, assuming that it can work, then we checked and found that it can produce a good amount of CO, H2, it can produce good H2, CH4, and with a reasonable CO2 and nitrogen with a good calorific value. So normally the calorific value of a rice husk or groundnut shell, they are all close to 5.5. But we found that this STW can give a good calorific value. So this is the prediction. We didn't use much computer capacity. With the basic equations, we can predict how it behaves. So this is possible for any biomass if you know the characteristics of the biomass. Okay. These are some other studies we made just to predict the behavior of rubber seed kernel shell, fire pith, coconut shell. All these things we used in this type of simulation. A couple of students worked on this, so all their works, if I present, it will be too much. That's the reason I am putting few slides just to show the trend. We can understand. For example, if I use different, mixture or different blend ratio, what I can see here is the higher heating value is not the same. So when we are mixing, it can either increase the calorific value or it can decrease the calorific value based on the equivalence ratio. Okay, so this will help us. If I want to take two biomasses, if I want to mix two biomasses, what percentage I can mix? 10, 20, 30. So to decide those things, this type of approach will be useful. Okay, if you go for experimentation, it will take a lot of time. You know about it. Numerical means it will take a lot of computer time. With the simple methods, we can test a mixture or blend. We can test a new biomass or new biomass blend. All those things are possible. For example, if you know in a place rice husk is available abundantly, but tamarind shell is only available limited quantity. So we can combine, okay, this is 5 ton available, this is 1 ton available. Can I put 20, 80? So we can take a decision whether it is possible. If I put, how much efficiency I have to compromise. So all these things you can study based on these approaches. Okay, even the gas production rate. The gasifiers are designed for a particular gas production rate. If I am reducing the gas production rate, then I cannot meet the requirement for the application. Therefore, that also should be studied. We have to study the gas production rate, at the same time the quality of the gas. When we increase the airflow, automatically the gas flow will increase. But because of the nitrogen and carbon dioxide, the quality of the biogas will go down. Therefore, we have to compromise. At the best condition, how the airflow rate or the gas flow rate can be maintained. So all these basic studies, basic idea, we can get from these type of analysis. Okay, conversion efficiency similarly. Okay, similarly conversion efficiency we can study. What I said, no, the basic parameters for taking a decision on the performance of a gasifier, we can use this type of analysis, right? It has a lot of advantages. Almost all the advantages I discussed in the presentation, but it has its own limitation. Okay, it has limitation mainly. The design aspect cannot be incorporated. So when we go for a gasifier, it has different size, shape, internal structure, everything. It is very difficult to incorporate all these things because the flow properties are issues, temperature properties are issues, heat loss is an issue. So all these type of issues are normally based on the design aspects. So it cannot be directly incorporated. That's the one major issue. Then the temperature distribution, internal heat transfer, those type of things, it's very difficult to model in the help of the analytical modeling. Then geometry, the reactor, reaction side, all the side, the geometry we need to specify. If some geometrical parameters are there, it's very difficult to use the analytical method. Then the problems because of the mixing of biomasses, the size of the things, the formation of clinkers, those things, the ash controlling, all those things, it's very difficult to analyze with the help of the analytical methods. Then equivalence ratio. It's also very difficult to predict the equivalence ratio because the curves you see, it is either going like this way or this way, something like that. It is not showing up and down movement. Equivalence ratio, if you want to find out, means best equivalence ratio means there should be an increase in performance, then decrease in performance. Then only you can find the best value. But in these analytical studies, it's very difficult to fix the spot. But experimentation we can fix. So this is the main drawback. If you want to find which is the best equivalence ratio, very difficult. But if you want to know the range, what is the probable range of the efficiency, all those things we can find, right? Then moisture. So the fluctuation in moisture, it's very difficult because when we operate the gasifier, the moisture fluctuates, when each lot when we put the moisture will vary a little bit. Accordingly, the performance will vary. The equivalence ratio varies. The gas production rate varies. Because we studied for 36 hours, 40 hours like that continuously. When we are charging the feedstock, we experience the variation. When I come to the experimental studies, I will show that to you. So there are a lot of limitations available for this, as I said, okay. Then the moisture, all these issues, some issues can be tackled by the help of the numerical analysis. So we concentrated a little bit on the numerical analysis. Even though the computer capacity, all those things were there, we tried with the numerical studies. Here I am just saying what is the reason the numerical study has been taken for our work. In this one, we can easily check the dimensional suitability. First one, we checked analytical method. We checked whether the process will take place. Yes, anything? Anything happened?
No, sir. No, sir. Please continue.
No, sir, you can.
Okay. So why we went for the numerical simulation? Actually, the numerical simulation has the advantage of incorporating the dimensional issues of the gasifier in our analysis. Okay, we can easily check the suitability of the dimension. All right, that is possible. Then the zone characteristics is possible. As I said, when we change the biomass, sometimes the nozzle position has to be changed, or the nozzle angle has to be changed. All those things we can study by the help of this numerical simulation. Even we can predict the tar formation, how the tar is formed. Okay, we can easily find the temperature distribution. We can understand the heat loss through the walls. We can easily verify the equivalence ratio. Previous studies, no, the analytical studies, it was not possible, but in the numerical study, we can verify the equivalence ratio. We can very well define the producer gas composition. The main thing is the numerical simulation. We take the energy balance, mass balance, and the equation, the kinetics, all these things together. We make thousands or lakhs of small control volumes. It means elements, no? Therefore, we can do all these type of analysis inside each and every one of the control volume. In the previous analytical method, we used 20 or 30 control volumes, and we tried with our approach. But here, we can go for lakhs and lakhs of control volumes, and each control volume, I mean element, we call it as element or node, whatever may be, we can apply all the chemical balance equation, energy balance equation, mass balance equation, all these things we can apply. So that is the reason we are able to get a better outcome regarding the temperature, the pressure distribution or temperature distribution, or biomass and gas distribution. Almost all those things we can get in these numerical analysis. Even the heating value, it's a derived one. Okay, but the producer gas composition we can get. The producer gas composition we can get. All those things are possible. That's the reason we started working with the numerical simulation. You may know what is numerical simulation. Just for the understanding continuity, I just want to say a few steps which are involved in the computational fluid dynamics. The computational fluid dynamics is a finite volume approach. Initially it was finite element, finite approach. It is a finite approach first. First people were using finite difference approach. Now the advanced software packages, they are using finite volume approach. It is a very good approach to find the variation inside the control volumes, right? There are many stages. The main thing is, if you want to do a numerical analysis, first we have to define the problem. We should define the domain, all those things. That is the identification, problem identification. We should take the problem towards a mathematical model. That's the main thing. Then we have to create the geometry. Then we have to create the small control volumes or mesh. Then we should define the physics. Physics means what are the chemical reactions going on, how the flow is happening, all those things we have to define. You know, CFD is a software, is a methodology which can help us to analyze each and every control volume, and all the equations, everything are solved by some good solvers. If you define properly all the parameters, the solver can give a good solution. So therefore, the physics should be given properly. The mesh should be selected properly. The geometry should be defined well. Then only the solution will be good. Normally, commercial software, whatever you give, it will give a solution. But the solution may not be good. If you define all those things, the solution can go to the right place. We can define the boundary conditions, solver. There are many solvers available. Depends on our flow domain. Because sometimes the flow takes a 180 degree, sometimes the flow is a straight flow, sometimes it is a high turbulence flow, low turbulent flow, or the supersonic flow. So depends on that, we have to set the solver. Then we have to solve. Iterative solutions are available. We can check the solution. There are many methods are available to check whether the solution is converged, whether we are getting the right solution. Okay, some methods are available to test. Once it is okay, then we can examine. Once we are examining means we can get different types of output. Okay, we can get different types of output. I'm just giving you how we defined our problem in a a software called Fluent. We used our analysis, we used Fluent for our analysis. Initially, we used Gambit to model the system. Later, we used the ANSYS workbench. There itself, the entire model was created. Then we used many solution methods to make the solution, right? These are the two gasifier types we used. We have to define more accurately, and we used the 2D model, okay, two-dimensional model, because if you go for 3D, we need a large computer processor, as well as in these type of gasifiers, they are having some similarity, okay. If they have a similarity, we can go for 2D analysis, that is okay. So in the numerical studies, if something is having circumstantially a similar arrangement, we can go for this type of 2D analysis. This will help us to give a solution close to 95% plus accuracy. That's the reason we selected this two-dimensional approach. This is a gasifier, okay, the model number 1, which is 50 kilowatt thermal. This is the model number 2, it is a 115 kilowatt thermal. This can use different type of feedstocks, either a bigger one, a smaller one, anytime. And this one can use only the particle bigger size biomass. And the other difference is, in this one, if you take, we can change the position of the nozzle. Actually, when the gasifier is supplied, it has a constant position of the nozzle. We can modify. If you take the pipe, a long pipe is there, if you take the pipe and we can change the position, change the angle, all those things we can do. So we changed those things even in the practical way as well as the theoretical way, right? So we can analyze the position, everything, all these things we can analyze. Accordingly, the domain was created, okay? We cannot create a domain differently and do all the analysis at the same time. Every domain we have to do a separate analysis, then we have to take the results. Similarly, this one also. And the difference is, this one, the air is supplied here, okay, this is forced circulation, here it is induced. We have a blower, it sucks the air. There is a difference, anyhow, I will tell you later. As far as the simulation is concerned, no need to bother about that. We use the model in the ANSYS, it is a two-dimensional model we used. We made the geometry, the design modeler of the ANSYS, then we used the analysis in the Fluent part of the ANSYS. The boundary conditions are very important. See, if you want to do a solution in a CFD software, we have to define the boundary properly. Some places we should give only velocity, some places we should give velocity and pressure. There are some limitations available. You cannot combine some boundary conditions, okay? So that we have to study from the basic guide of the software, and accordingly we have to define. We found that mass flow inlet is good, pressure outlet is good, and we defined all the wall conditions. What type of wall is for a simple analysis we can go for a diabatic wall, then sometimes we can put a constant heat flux wall, something like that we can give. Some places we can give flow velocity inlet, we can define. And the models, we have to think about the turbulence model. We can go for the turbulence model, K epsilon is a common one. In that we selected RNG, okay, a renormalized grouping. There are different turbulence models available. Among that, we found this RNG is good because our flow is taking a full 360-degree turn. Inside the gasifier, the flow goes up and coming down. Therefore, there is a turn of 360 degrees. So normal K epsilon model may not support sometimes, and it was not giving a good value also. Therefore, we took the RNG model and solval algorithms. Different algorithms are available, okay, simple, simpler, etc. Depends on the problem, depends on the complication of the domain, we have to go for different solvers. For us, the simple solver is enough, so we took the simple solver method. And for the combustion and reaction, we should take the right model. We used the 3C transport model. Okay, this is the one which is more suitable to define all the species as well as their reactions. Okay, anyway, let me show you the next slide about the reactions involved in that. So these are the reactions. So in the software, we should know all the reactions. The software will not say this reaction. We should give all the reactions. That's the advantage. Any reaction, if you feel, we can give. The potential of the reaction is defined by the pre-exponential factor and activation energy. It will show how the reaction will happen. Once we give all those things, the software will create a file, something like that, a probability distribution function or something it will create, and it will think which will happen more, which will happen less. So all these things are decided based on these type of things. So we can define the equation, we can define their kinetics, everything by the help of these type of constant and other things. Many components are available. If you define all those things, any biomass can be defined well in the software. Okay. This is the general simulation what we used. First, we have to create the geometry, as I said, just for refreshing the whole thing. Then species transport model we have to select. There is a model, some constants, everything is there. We have to revise and we can define exactly. Then we have to define all the species, all the boundary conditions. Then we have to go for the model, turbulence model, and we used SC dissipation model. Sometimes we can define a porous media to define the pressure drop. We can go for porous media. So all these things we have to define. Then we have to go for the run. When we go for the run, the major problem we face is the stability, or we don't know whether our solution is good, whether our discretization of the domain is good, whether the domain is taking care of all the flow properties. For instance, if some places there is a twisting of flow, we know the twisting may happen to this much 1 centimeter or 1 mm or 2 mm. So our element size should be less than that. Then only it can incorporate the twisting or changes. Okay. Otherwise, no, it will not take care of those things. So we should define exactly the element size. So how to define? Normally people used to do all those things, they won't make the checking. The one important checking is the grid independency check. How the grid is matching, you know how there are two types of errors coming in the CFD. One is round off error and truncation error. Depends on the number of elements, the round off error and truncation error will change. Okay, so we have to balance. If the two errors are balanced, then you can get the good solution. How to balance? It is based on the number of elements. Okay, if more number of elements, if you put that, don't feel that you will get a good result. No. Sometimes no, the round off error will dominate and it will create a big problem. Okay, so therefore we should know what is the good number of elements. So that we have to check. First we take 1 or 2 parameters. For instance, when we are using that, we use the CO and H2. They are the main producer gas compositions. So we used CO and H2, carbon monoxide and H2, and we checked the combustible gas composition. When we increased the 25,000, first 25,000, 50, 75, like that, when we increased, after some, if you say the value is increasing, after that it is becoming stable. Similar also, it is increasing and becoming stable. So we observed that, okay, this range of elements are okay. Okay, this is the way we have to define the elements, right? Then we have to check the skewness factor. Whether all the elements are with the proper angle. Yes, we define rectangular element. The element angle, if it goes above 120 degrees, the skewness will be high and the solution may not converge or it may not give a good solution. And we should check sufficient elements are available in the important places. For instance, if you take the combustion zone, next to the nozzle, the combustion takes place. There we should put a lot of more elements, no? Because that is the area the chemical actions will be very fast. So to define those things, we need to have a right element number. Okay, if it is a very coarse, then the solution may not be very fine. So then first we are checking like this. Second thing is we have to check the experimental results. Let it be. But anyhow, when we are defining the domain, for example, if you take the domain here, this area, a lot of activity. So we need to have more elements here. Likewise, the reaction zone, we have to have more elements. But if you take the drying zone, no need for much elements. Likewise here also. So wherever we need to bother more on our analysis, we should give more elements. Then second thing is, people are now saying that any type of element the software can take, but if you can manage a uniformity in the element, uniform in the sense, shape, everything, it is uniform, then you can get some good results. That is also an important factor. Sometimes we do all this modeling, but may not give a good result. This is because of the uniformity in the mesh. Okay, that you have to adapt. Once it is over, we can say that our solution is good. Then a lot of converging factors are available, and relaxation factors are available. All those things, it is defined based on the previous studies and experiences. Okay, similar studies, people will say this type of control is good, because if you go in deep, if you read the ANSYS manual, you can get what is the reason we have to put 0.5 as a relaxation factor. If the turbulent model is this is the good relaxation factor. All those things you can get it from the literature, and if you apply, then you can get the solution. So once you get a solution, now we can change any part. The angle can be changed. This is for the nozzle inclination. If you want to change the nozzle position, if you want to change the biomass properties, we can change. Okay, once you go for a standard property, then only thing is as I said, no, these values will change. These activation energy may change, the exponential factor may change, the additional equations may come. Okay, all these things, if you are mixing biomasses, different type of biomasses, sometimes we can experience different reactions. So those things can be incorporated, then we can predict the properties. Okay, actually the CFD, creating the model, defining the physics, solving is tough. Once we finished and we found the results is okay for a particular domain, because the domain is very important for getting a solution. The solution is based on the size of the element, the skewness of the element, the independency of the element, all those things are very important. So once we get a solution for a particular domain, then we can change any property. It may not deviate much from the actual values. Okay, so once all these over, then we have to validate with the experiments. End of the day, if it is not validated with the experiments, we know it's difficult. But for initial decision making, we can use these analyses. So first we can go for the analytical studies. Okay, if we found it is good, then second stage, we can go for the numerical analysis. We can get some more accurate results. For example, if you go this one, see, you can get the temperature distribution. This is one sample for the one gasifier. I can get the temperature at any place, any equivalence ratio. See here the angle is, we can experience, no? Here, no? The angle is 0 degrees inclination. It means it is straight angle. See the temperature distribution. If it is angle is changed, this is a distribution. It is changed, again the temperature distribution. So all these things say that there is a role for the nozzle. There is a role for the position. There is a role for the shape. Even if you change the shape, the temperature will be different. So with that we can find out what is the temperature, we can find out what is the maximum temperature in Kelvin. We can get 1000 to 50 Kelvin, the maximum temperature, the minimum temperature. So all these things we can easily observe from this type of analysis. Okay, because the temperature is a very essential one to control the entire operation. If temperature is very high, as I said, it will create a formation of clinkers. Sometimes it will spoil the refractory material. If some hot zones are coming up, the refractory material will fuse sometimes, or the wall will get affected, or cracks will form. Therefore, we have to take care of the temperature distribution, one important thing. Then all the gas compositions we can study. I am giving you one example. For instance, CO distribution. The previous studies we don't know exactly where CO is more, where CO is less. Here we can say the CO concentration. Even though this is the end, but the CO inside is not same. You can see that different angle position, the CO concentration is different. So some positions it is different. Okay, so we can understand, okay, which position, how much CO, which position, how much tar will happen. So all these type of understanding we can get. and how the flow happens. Where the gas means how it is going, what velocity goes up. So all these type of structural activities you can observe from the CFD analysis. If you go for a 3D, it will be more accurate because we are assuming that the circumference is okay, similar. But if you go for the 3D approach, you can find more accurate results, but we need to have a larger computer space, and the flow domain definition, model definition, solver definition, everything will change. Don't think that in a 3D model we have to use the same methodology. May not work. We have to define accordingly. But basic definition is same. The equation definition, the kinetic energy, all these parts, no, it is same. But solution controls and the other models, solution models, everything, there will be change. But you can get a better solution and you can predict well. Here, we checked the theoretical and experimental. Actually, in the theoretical way, we made path lines. No? These are the path lines, and we made the positions. We checked different positions. Once we know the numerical analysis result, from that we can find the value at any spot. If you have 1 lakh nodes or 2 lakhs nodes, each element or each node we can take what is the temperature, what is the pressure. So we put some spots and we checked because we have our temperature sensors. We kept the temperature sensors inside the gasifier, and the different spots are already fixed there, positioned there. Those positions we checked, and these are the experimental values, and this is a theoretical value. So we found almost matching. Again, some refinement is needed. All these places, no, it is not matching well. So therefore, some refinement might be needed. We took only the average. So there may be some refinement needed, but still it is holding good because the starting point and the end point, we are getting some good results. So this shows that the numerical approach, if it is done well, it can help us to find how exactly the system will work. Similarly, this graph, which is showing that the nozzle inclination and the higher heating value. Okay, higher heating value we have checked, and this also for the positions. We checked for the inclination, we checked for the positions. So we can see here, at the inclination of 40, this place, 44, 45 degrees, it is good. And the position around 100 mm from the one position, from the, from that reaction zone beginning, from there we fix the position. So the position is good, this is good. So all these things we can get by the help of our numerical studies. Right? Now here, we can compare with the analytical results. See, this is analytical result, this chart. You see here, the higher heating value is going down drastically like this. But if you see here, calorific value or higher heating value, whatever may be. At low equivalence ratio, it is low. When the equivalence ratio is increasing, it is increasing. Then after a particular limit, it is falling down. So it can help us to find which is the best equivalence ratio or range of equivalence ratio. It's very difficult to fix a single equivalence ratio. Small range will be there. It is all for all these things. Moreover, it can tell us what is the best equivalence ratio for different biomasses. For instance, if you take the coconut shell, this is the best equivalence ratio. But if you take the other one, this one is rubber wood, this is the equivalence ratio. Okay, so each one, the equivalence ratio may not be the same. For example, this one, this is the equivalence ratio. This is for the rubber seed kernel shell. So each one we may get a different type of equivalence ratio. So this will help us. One idea, okay, how the equivalence ratio is changed, how the calorific value is obtained, which is the best equivalence ratio. All these things we can identify. Whereas in the analytical results, we cannot get that conversion. So already I told you in the beginning. This is another gasifier. Here also the position is checked. Okay, the position is checked 0 degree, and the CO composition is checked, and we are able to understand that the CO composition is some places it is high, some places it is low, but the outcome it is coming in particular quantity. Okay, so the distribution can be easily obtained. So any gasifier, if you want to use for a particular application, for a particular biomass, we can easily predict with the help of the numerical studies. We also checked with the experimental analysis. Some nozzle positions only we are able to change. Those we found that the deviation is not much. All the places in the experiment also we found some degree it is good, and numerical also, even though this is good, here this is good, right? Some values are very close. So it shows that the numerical prediction are almost close to the experimental observations for a particular type of gasifier, right? This is the combustible gas composition. All those things we studied and found good, but it has its own limitations. Okay, it has its own limitations. It take more time. No, we are modeling and analysis, a lot of trial runs. We need large computer capacity, and the transient simulation also we can, but all difficult. No, but if you want to go for a rural application, we cannot invest a huge money for those things. So such things, it has a restriction. Okay, and the flow issues, again, the biomass gasifier, the major issue is the flow issue. When the moisture goes up or moisture goes down, the flow will change. Yes, the gasifiers are designed for a particular condition or a range of conditions. So when we change it, a lot of variation, but that cannot be predicted well with the help of this numerical analysis. Okay, mixing issues. When we go for a bigger size particle and smaller particle, as I said, I want to have wood chips, I have rice husk. Can I mix it? How? How it works? We cannot. But in the numerical way, it will work somehow, but practical point of view, it may not work. But some biomasses can mix. So that type of things we cannot. And so same thing, clinkers. You know, clinker means it is a kind of carbon, it's a melting of ash. The ash melts and it may form solids. It's very difficult to remove it. The major issues we are facing in the gasifier operation, even we faced problem also because of these clinkers. Sometimes if that is not controlled well, if the gas flow rate is increased, immediately the temperature shoots up. If we are not controlling that well before switch off, the clinkers will form. So a lot of issues will come. Therefore, that type of formation where the clinkers will form, all those things we cannot predict. We cannot predict also the unburned biomass, what happens to that. Yes, when we clean, when we clean the ash cleaning mechanism, sometimes we can see a lot of carbon, charcoal comes out, small parts of charcoal. So that cannot be predicted. All these things, we need a experimental study. That's the reason we took the experimental study. The experimental study, we used 2 gasifiers. As I said, this is one gasifier. So this gasifier, if you go to this, see, it has a top, we modified the gasifier, this area we modified to put all the thermocouples inside. We had a special tubing arrangement because our inside temperature goes around 900 and 1000 degrees centigrade. So that temperature, the probe should not melt. So we use separate refractory coated probes to keep in different places. Okay, these different places is kept. First we have to upload, load the things 50 kg or 60 kg we have to load here. Then these are the places we can see. This is the blower is just sending air, and we have to ignite through this. And here is the bottom. This is only used for a batch processing. This mainly actually this gasifier is used in crematoriums. For the grounds, crematorium grounds, it is being used. And here there is a tank. It is for thermal application. So no much cleaning, everything is needed. Directly the biomass, the producer gas comes out. All the ash is collected in this tray. This tray collects all the ash. Then the producer gas comes out. It has some tar. Since it is high temperature application, immediately the tar will go along with the gas, because tar will sediment when the temperature goes down. If you want to reduce the temperature of the gas, definitely we should clean it. Otherwise, directly you can use, because high temperature, the tar is in the volatile form, so it will go along with that and it will burn in the burner itself. We cannot use the jet burners. We have to use open burners. No, the burner is different. If you go for other type of industrial burners, it is not possible. Since it is for a open firing or brick firing or some kiln firing, those type of firing, it can be used because direct firing. No, in between there is no bottleneck. If a bottleneck is there, immediately there will be choking because we try to install some measuring instruments in between that flow area. After a couple of operations, we found the entire area is choked. Because the probe what we inserted that created a hindrance to the flow. Because of that, the tar formation happened. Therefore, some issues are there in the operational issues. So we should fix the measuring instrument, everything accordingly. Then we use the cooling. After that only we measured many parameters, right? This is what the one. This one is a gasifier we used is a bigger one, as I said. Here the hopper is available. We can put the biomass inside, and this is the area the pyrolysis zone, the combustion zone. This has a lot of arrangements. It has we can take the hot gas directly. We can take this has a scrubber unit to clean the gas. You know, the scrubber unit, then lot of filters, chimney, everything is available. If you take this motor, since we are using rice husk or groundnut shell, we have to shake it frequently to maintain the flow. Otherwise, the flow will be choked. So we are using this vibrator. Same way, we have to clean the ash frequently. So cleaning the ash, we have a cleaning mechanism. Since we have the cleaning mechanism, we should have a cooling tower to control the temperature of the water. Okay. Okay. So these are the two things we used. So we have to control so many experimental issues, right? The bulk density created problems, moisture control, equivalence ratio, the particle size, homogeneous mixing of biomass, the temperature control, control of clinker formation, handling ash, gas cleaning measurements. All these parameters are the controlling factors in the experimental analysis. Okay, so I am not going to explain all those things because I have a couple of minutes to finish my talk. This is one experimental setup, which is I said one setup which has a capacity of 50 kilowatt thermal. We initially we measured. Sometimes then we used all these things. Mainly we used gas analyzer, gas chromatograph. Yes, we used two things. Sometimes the gas analyzer may give a wrong value, so maybe the calibration issues. So we use gas chromatograph for crash verification. Both the things we are used to measure all the things. And this is the setup for the bigger gasifier. Here we have used many temperature sensors, and all the places we put a lot of measurements, gas analyzer. Yes, we used this for different applications. One application we used it for the kilns. Mainly our area is having a lot of pottery kilns and clay brick kilns. So our aim is to use this for the kilns. Maybe we use sometimes directly or this, because for the analysis purpose we used all the filters. Otherwise all our instruments will be choked up, and we have to use the nozzles, okay, burners. We started using with the direct firing. Because of the choking in the burners, we used the clean gas, and we try to find out how far it is economically viable. Then we used in the engines, IC engines. Then these used for the paddy parboiling. So all these applications, the gas was tried. Okay, whether the producer gas quality is enough. We used different biomasses, local biomasses, different mixtures. When we use, how the system performs, how much the quality we maintain in the application. Because once we used some material, some biomasses, the brick quality was not good. Some biomass, especially when we used that coconut shell, the quality was very good. But when you use rice husk, the brick quality was not good. Maybe the calorific value. But in the case of engine application, there was not much difference. Okay, because it was balanced, and the efficiency point of view it was okay. So we used all these setups. And because of that, we were able to identify the higher heating value. You see, higher heating value is not same for all biogases, all producer gases. Depends on, this is coconut shell, rubber seed kernel shell, rubber waste, rice husk. When we use different material, we can see the higher heating value changes. Therefore, the higher heating value will change based on your biomass. You should study that experimentally to prove it. But you can get something in the numerical and analytical studies, but experimental studies give more accurate value. And it is not stable. You see, this graph says that the higher heating value for a particular application, this higher heating value, we worked the gasifier for 36 hours continuously. In between, see how much it is fluctuating. So all these things are happening because of the biomass loading and the quality of biomass, its moisture content, and the flow issues. Yes, whenever the issue happens, immediately we have to switch on the combo rotor, or we have to switch on the vibrator, something we have to do. So all these things will happen. So we have taken only the average values. Similarly, equivalence ratio. You cannot say the equivalence ratio is same, but it is in the range. We checked it, it is in the range. So we can say that, okay, this is the average equivalence ratio, we can get a good result. Okay, and the gas production rate. It is also important. When we put a new biomass, we should not disturb the gas production rate. If it is reduced, naturally the techno-economic viability will go down. We cannot get a required quantity for our application, because our one gasifier, it can produce 80 normal meter cube per hour, and it has to operate at least 60 or 50 normal meter cube per hour. Then only it can give the required efficiency, required techno-economic value. So all these things we can check by the help of this type of experimental analysis. Okay, and then as I said in the beginning, when we use STW, spent tea waste, when we use, it can enhance. So what we did, we checked. The numerical study says that it is good. Analytical study says that it is good. But we don't know how can we mix it or not. So we took the rice husk and groundnut shell, and it was mixed with this tea waste. It has a lot of moisture. The advantage is when we mix with this bio waste, it can easily stick with the biomass. It can easily stick with the coconut groundnut shell. When you mix it with the water, it can easily stick with the groundnut shell, and it showed an enhancement in the efficiency. This table shows that. Okay, this table shows the first one. Here rice husk alone we used. Here this says that this is groundnut shell. Where we mixed around 40%, 30 to 40% of this spent waste, we can see the increase, around 16% improvement in the calorific value, old gas efficiency 14% improvement in the rice husk. The groundnut shell, when we checked, it was around 10% improvement in almost all the values. So this shows that within the available limit, when we add some quantity of this powdery biomass, there is a possibility to enhance to the gasification potential. If you take the rural areas, we have different types of biomasses. Their particle size is different, quality is different. Sometimes, if you take the right mixture with the right quantity, you can. So the entire way is, when you take a biomass, first we have to go for analytical analysis, then if possible numerical. After controlling all those things, if you come to the experiment, it's good. Otherwise, we cannot predict that it will work well or not. Sometimes, if it is not giving a good biogas generation, if the producer gas generation, choking will happen. The gasifier chokes is a very big problem to rectify it. So this is the basic analysis we did. Actually, we used the biomasses and we found how. Then after all these things, just like that, we cannot finish it. We have gone through the uncertainty analysis. It is also made us to change our instrumentation. Sometimes the instrumental accuracy is not sufficient, means we have to change. That is the reason we went gas analyzer and gas chromatography, right? Then mass balance. So a lot of equipments we used to do the mass balance, energy balance. Then the statistical analysis of data. As I said, I showed there is a large variation in the data during the running time sometimes. So we made statistical analysis of the data. Okay, then we checked the ash generation. We used special ash collecting agent methods to collect the ash, and we used collected the unburned feedstock. Okay, then we energy balance. We measured the temperature of the water going in and going out. Yes, we should know how much heat is wasted. So all these things we studied, and after that only we came to know that there is a good potential for using multiple biomasses for the effective gasification in the rural villages. Okay, even we increase the temperature. Even we increased the temperature and found, for example, here we increase the temperature of the inlet here. I will show you a picture. Okay, even we tried the inlet air temperature. So when we increase the temperature, some extent it was doing well. After that, it was not good. That also we checked, but we didn't do the energy balance. Okay, because if you give energy for the preheating, it may not work well. The energy totally it is not worthy. So if we have waste heat, we can use it. So based on that, we arrived at so many conclusions. Each paper we have different conclusions. I'm not going to elaborate all those things here. If you go through our publications, you can see all the conclusions for different aspects, right? Generally, you can say that groundnut gasifiers are suitable to work with the biomasses available in agricultural areas, especially what we checked. It can work very well, but with some strategies we have to maintain. And we are able to establish a good numerical model to predict the suitability of the dimensions. Okay, co-gasification is the best one, which is suitable for implementing the biomass gasifier in widespread rural applications. Of course, the government of India or any government, they are going to give a lot of industries and other things to the rural areas. They are planning for decentralized power generation. All these places, if you use the biomasses in the local area with the help of this downdraft gasifier, you can make electricity or you can go for thermal applications. Definitely the techno-economic and other studies are needed, and proper survey is needed, and regional wise survey is needed. Okay, because the selection of biomass is different for different regions. Therefore it should be, and the techno-economic value is also not same. If you go for the hilly region, there the requirement is different. If you go for the plains, it is different. There the cost is different, other places is different. There the need is different. If you go to the forest area, if you in our place, some places, all the time we can see shading. We cannot put this PV module there. We cannot put a wind turbine there because the tree shading or the wind disturbance. If you put a windmill, all the trees and mountain area nearby those areas, they will create a lot of turbulence and the wind energy will not be produced as expected. So other thing is birds and other things, they spoil, echo will be spoiled. But if you go for this biomass based thing, definitely the rural application can be tackled with the help of the biomasses available there. Meantime, we can contribute towards the energy transition expected 2050. Okay, so a lot of opportunities are there. People should start working on that. Then definitely we can come out with good outcomes, and it will be useful for the entire humanity. I know we are now bothering about the magic value 1.5 degrees centigrade global warming temperature. So we can work something towards that, and we can give our contribution to protect our environment. Okay, these are our publications. A few publications I have given. You can also go through. Even if you go to my Google Scholar page, you can see all the publications. You can take it from there. If you need anything, you can collect it from us, no problem. And you can study more and you can do well. Okay. With a few words, I'm ending my talk. Thank you very much for your patient listening. Now you can raise your questions and all. Thank you.
Okay, sir. Thank you very much for the informative section, sir.
Okay.
It's a very informative for in the numerical parts and experimental parts also. Thank you very much.
Okay, thank you.
Thanks.
Thank you very much. Good luck to everyone.